Okay guys, in our last video we looked at the relationship between inverse functions, and basically what we see is that one function gets sent over from an x to a y, and then the other function takes that y and sends it back to x. So essentially the inputs of the original become the outputs of the inverse, and then the outputs or the range values of the original become the inputs of this inverse function. So what we see is that the domain and range switch. Okay, this is so important that we know that that's the relationship here. The reason why I say that is because what I'm going to ask you guys to be doing is finding these inverse functions. So we say find the equation for an f inverse of x given some f of x, and then verify that they're actually inverses. So here's what I'm going to do. Recall that what we want to do is basically switch our domain and range. So my advice is, first of all, I tell everybody, let's just go ahead and switch our f of x out for a y, or whatever we have, function of x for a y. What we're going to do is, we're basically, again, from the notes you should have seen, we switch x with y. And so if I do this, I really just get x equals y plus 3. Hey, this right here is disassociated with the original. This is its own inverse here. Basically, these are different functions, and you've already found the inverse. It's just that, remember, we kind of like to write things in y equals form. So the last thing I need you to do here is just isolate y. In this case, we would end up with y equals x minus 3. So I'm going to put a big box around this. And also, we're going to rename y here into f inverse of x is equal to x minus 3. We'll put a big box around this also. How about a bigger one? Because I like this notation the best. And so we started with some f of x, and we end up with this f inverse of x. So pretty neat. I think that you guys probably think this is rather reasonable to think that any function that takes its input and just adds 3 to it, well, of course, then the inverse function would say, take that input and just take 3 off of it. And so that being said, I think this brings up a really important graphical consequence here before we find the next two inverses. And that's to say that if your domains and ranges switch here, we have x minus 3, we have, I'll put g of x equals x plus 3. There's a couple of linear functions with y-intercept of 3 and negative 3, and they both have a slope of 1. But looking at these here, we see that all the points on the original graph, if I were to take 0, 3, okay, it's kind of like when we looked at this table of values here, x and y just switched around. So if you look at the graphical significance of this, if you were to look at a table of values here, not table of values, here we go. What would happen graphically to these graphs here? 0, 3 becomes 3, 0. There we go. 0, 3 is 3, 0. 0, negative 3 on this graph becomes negative 3, 0 on this one. As a matter of fact, all the points flip over. And so what I have to tell you is basically that we have this line y equals x about which our graphs are symmetrical. So let's remember that here as we look at our next couple of functions here we find inverses of. So hey, really quickly, hey, you know, you got a function, you want to find its inverse. Let's go ahead and switch out our f of x for a y here. But basically, you want to find its inverse, you just switch every x for a y and every y for an x. You're going to have switched the domain and range. So here is our inverse right here. And what I want to do is just isolate the y value. So let's add 1 to both sides. It's okay if we write this as a fraction. We say x plus 1 is equal to 3y. And I'm okay, with writing this as x plus 1 over 3. And as a matter of fact, that's okay if you want to write it that way too. I would encourage it for this course. And so we would say that this is f inverse of x, big box around this. And we think that this is the undoer of this function here, okay? So the last thing we were supposed to check is, hey, whether or not these are actually inverses. Because I have f and f inverse, let's go ahead and do this. We'll find f of f inverse of x right here, as we've been asked to do, f of f inverse. And this means that we're going to plug this function down here into this original function. So if our original function is take what you plug in and add 3 to it, well, what we're plugging in is f inverse of x, which is really x minus 3. So what we see here is that our x's cancel out, our 3's cancel out, and we just get x, which means, hey, all the y values of this function, when you plug them into the inverse, they go back to the x value. So this would be enough to prove that they're inverses. No need to check f inverse of f of x, even though we've been asked to do it. So taking a look at this last function down here, I want to look at a function that we're just kind of learning about its parent function, its basic shape of a cubic graph. Let me go ahead and graph this for you here so you're not worried. Not sure what I'm talking about here. Y equals x cubed is one of our parent functions that goes through 0, 0, goes through 1, 1, goes through negative 1, negative 1. As a matter of fact, it's an odd function. And we see that 2, 8, negative 2, 8, given this function here, we want to find its inverse. And remember that graphically speaking, all the points on this graph here are going to flip over, and what we're going to get something is behaves as a reflection of this graph on the other side of that line here. But when we look at this here, what would we expect to get? Well, interestingly, we're going to get one of our new families of functions as well, not the cubic function, but the inverse of cubing something. So think about this as we work through this. What would be the inverse of taking something and cubing? What would undo cubing something? What's the inverse of that? So first things first, easy enough. We're just going to take our y and put it in place of f of x. Let me fix that mutated 3 there. And so we're going to switch these out. We say x becomes y becomes x. Sometimes you have more than one of each, okay? We switch them all out and we got to get y by itself. So first things first, I don't see that I have like a +2 or a 3 in front here where I'd have to subtract the 2 and divide by 3, okay? We just have a plain old thing that's being cubed. So if that's the case, we can undo it. And that question I had asked you, what would undo a cubed? The answer there was a cube root. And so what we see is the cube root of something cubed, those would cancel out, and I just get y plus 2. And on the left side here, we just get just the positive, since it's a cube root, of x, okay? And so that there presents our cube root family of functions, okay? And subtracting 2 from each side, we basically end up with y equals the cube root of x, okay? That minus 2. So I'm going to throw a designation around this here, and we're also going to rename this. We say that this is f inverse of x, and we think that it's equal to the cube root of x minus 2. So before we run off and look at the graphs, what I want to do is find f of f inverse of x. And you don't always have to plug f inverse into f, but basically I'm going to do that here. And because my original function here is, let's see, we got a cubed, we had a +2, and we were plugging our stuff into this spot right here for x. And so because what I'm plugging in is f inverse of x, that's equal to the cube root of x minus 2. I'm going to try to squeeze this in here. Cube root of x minus 2. Hey, there go your 2's. So I'm going to simplify this. You should take your time, rewrite it, okay? You basically just get left with the cube root of x on the inside of this. And look what's going to happen when you cube a cube root. You're just going to end up with x, meaning that, hey, when you plug the outputs of this into its inverse, you got back to the inputs every infinitely many times. So let's really quickly take a look at the graph of this here, this f inverse of x. I said I wanted to compare it to the original. We get the cube root of x minus 2. So you're just going to have to trust me on this one right here. To write my cube root, I'm going to have to write x to the 1/3 power. But there's my cube root of x. So you can see our cube root parent function, and I said minus 2, minus 2. So if I were to say, okay, minus 2, we had x plus 2 cubed. Let's see if I type this in correctly here. Nope, I just had x cubed. I better put x plus 2 cubed, which would shift our graph 2 to the left. Okay, so we get our cubic function shifted 2 to the left, and we get this basic shape here. You could see that these are definitely reflected about this line y equals x, and picking on individual points here, suppose -2, 0 would imply that 0, -2 would be on this graph here. And we could take it a step further if I said 2 comma -0.74. Well, -0.74 comma 2, let's see if I can even find this here. -0.74 comma 2 would be up here. So you could see that switch in domain and range. So important that you guys can find an inverse just by switching your domain and range, or in other words, switch x and y around and get y by itself again. But also verify it graphically, which we'll lean on a little bit more heavily in the next examples. Cheers.